So in this video, we're going to talk about problem solving, the way uh, artificial intelligence, AI, looks at problem solving, one of the most common uses of AI. So what we have discussed so far are the few factors that contribute to intelligence, okay, that demonstrate intelligence. We've seen certain examples. And problem solving is considered one of the most important aspects in general human intelligence as well as artificial intelligence. So we considered the maze search problem of the mouse. So it needs to go from one place to the other. And there are several steps or paths or options available in that. And what the mouse tries to do it, get to the end where it wants to be as quickly as possible. So it has to make those decisions. So in general, it was believed that a person who can actually solve more problems is a very intelligent person. And in many ways, this is correct as well. Okay. So the more problem you can solve, that means you can think, you can decide, you can reason about things, and so forth. In order to understand intelligence, and this characteristic, problem solving, exists in all walks of life with human beings as well as the animals that we come across. So they actually perform the same thing. They're trying to solve their problems. Okay. One of the most classical approaches used by everyone, in the maze case also, searching for cheese, that animal has a limited intelligence. Okay. And it cannot actually think ahead and plan, so forth. What it does is it takes a random movement in one direction, comes to a stop, still looking for that piece of cheese, can't find it, looks around, maybe comes back, takes the first option, goes there, and then keep on doing this until it reaches the end where it wants to be, which is like searching for the cheese. So this classical approach is like a random approach, okay, which we call as trial and error. We don't think much about these things for smaller problems, trivial problems. So we try and do a random kind of thing, and what we call as mostly trial and error, hit and trial. Okay, try it, if it works, fine, otherwise try this thing. If it works, fine, otherwise. So we try and do this in many situations in everyday life. And as I said, in the maze search, this is what the mouse is trying to do. Let's look at another problem. Here's a toddler, a young kid, and it wants to enter and goes into a room which is dark, and the toddler knows that there are a number of switches, and one of them will light the switch bulb. So he wants to go to that. Now this child, the toddler, it doesn't have too much intelligence, so to speak, right? So it does a random search, tries to switch the first one, and it might land on the first one or the second one or the third one, depending upon where his hand lands on the switchboard. So it tries to do that, and doesn't work, attempts another one, and so forth, right? So this is what it's trying to do, is do a classical approach, hit and trial. So this is one of the characteristics. Okay, toddlers do it, we do it otherwise also. Consider, have you ever tried opening up a briefcase with a number lock on it, a combinational lock? Once again, if you were to do that, what will you do? You don't exactly know the exact combination which will open the lock. So what do? You try out a few random things. Like, for instance, if it's a 3-digit combinational lock, you try 000 or 111, 777, 786, and so forth. This is what you will do initially. But then you will soon realize that if this is not working, I need to do some more systematic things. However, this approach that you use every time, that's the classical approach. And a technical term used for this is generate and test. Generate and test. What does that mean? This means that we look at the problem, we start somewhere, And then we say, all right, let's try out this combination. So this thinking generation of that combination, okay, is a generation of a potential solution. So when we say generate and test, what we're saying is generate a solution, okay, and then test it. So generate and test, right? A very simple, straightforward approach. And this is exactly what we're doing. The mouse did it, animals do it, we do it. Try out a solution and test it, right? So this is why we call it generate and test, classical approach, and so forth. What I've done is I have tried to put this in the form of a diagram for you. So if you look it up, I've shown a small diagram where we can see this kind of structure. On the left, we have a box called solution generator, and then we have something called a tester. And then we've got a bucket where we keep on storing the incorrect solutions. It's another bucket where the correct solutions are being stored. So if we look at that, what we have is solution generator is something that comes up with each combination of the combinational lock. That combinational lock is your generator, so solution generator. And what does the tester do? This tester will actually try and open up the combinational lock. That's what the tester is doing. So combination of 000, for instance, okay, it will actually set those numbers to 000 and try to open up the lock. If it opens up, that's a solution. If it doesn't open up, you forget about it. You put it in the incorrect solutions. Then you generate another number, 111, as it said, 786, and so forth. So this is the setup of a generate and test strategy, just to give you an idea how we are working on it. Okay, and this can be a machine, it can be a function. The solution generator, it can be a function also, and so is the tester also, okay, which checks whether it's a solution or not. In terms of software, these are both software functionalities. Physically, yes, you have this combination lock, and your mind is thinking how to generate numbers, and then you actually physically go and try it out. So, the importance of these solution generator, tester happens all the time and so forth, and then applies to the maze search problem. So one of the key things that we need to understand also, when we're trying to put things on the computing side, okay, we need to find how to represent those things, okay. And so we come to that also. But one important point also, that we have considered, trivial problems, very simple problems. But when we're talking about more complex problems every day, for instance, you work at a university, at a college, and you're required to generate a timetable, a sheet for people attending the classes and courses. Now, this cannot be done. This problem cannot be done with a simple hit and trial approach. No, it won't work. You look at a problem, think about 5 minutes. You have 4 years, or let's say 8 semesters, okay? And then you have several subjects. Each class is zone, say 5 each. So you've got, 8 semesters, 8 groups of classes, each having sections. And then each have their own set of subjects, and then constraints, and so forth. Now, this problem cannot be attempted simply by trying out, let's try this, no, it won't work. Okay. So you have to then think of something more systematic, right? So what we're saying is, starting from a generate and test, hit and trial method, right? You come to a more systematic approach. And that's one of the important lessons. And then, in order to be able to do that, you must define, think, conceptualize the problem. And that conceptualization is what we call your mental representation, and then going on the piece of paper. That is a good representation. A good representation can actually simplify your problems. They can simplify your problems to a great extent. And this is what we call as conceptualization in general as well. you have a complex situation you are thinking about, and then you try to conceptualize. There are 3 factors here, 2 factors here, 1 factor here. You're trying to satisfy each one of them. So the moment you conceptualize, you think you have, solved half of the problem. So that mental picture and the toddler problem and all of that, these are trivial problems, but then more complex. Here's a diagram showing a representation of this toddler problem. Okay, trying to open up a switch in a room, a dark room. Okay, and there may be several switches, and what it does is, and each one of these, as you can see, for instance, you can represent the problem as a tree. Now, in fact, the word is inverse of a tree. The tree actually grows upwards, but these trees that we're talking about in computing, when we come across, they actually travel downwards. So think of this as an inverted tree. So you start from the level where all switches are off, and the toddler comes in. That's your starting point. The toddler comes in, randomly switches, presses one button. So this brings us to another state of these buttons represented in the graph. So each time the toddler presses one of the buttons, it creates a new situation on that graph. And we actually travel downwards in a way on that tree that we are talking about, the reverse tree that we talk about. So in general, it keeps on trying various combinations, and the tree goes on, expanding downwards until the switch turns on. And that's when the boy stops, the girl stops, the toddler stops. Okay. Now, having said this and done all this discussion, now I think we are rightly poised to come to a very, very interesting concept, and that is of a problem space, solution space. Okay. So we need to, let's formalize a little bit problem solving. This was non-trivial, and when we need to do more serious kind of problem solving, we need to formalize. So we need to first of all constitute what is the problem. Okay, what is the problem that we're trying to solve? Call it as a problem statement. Okay, a problem statement. Then we also need to know where we are and where we want to go. Okay, so in search, and we keep on talking about this, you will keep hearing about it. Search means you need to move from some place where you are and you want to get somewhere. Okay, so that means you need to travel. Okay, so you need to start somewhere. Okay, and you need to end somewhere, which is your goal or solution or something that you want to resolve. Okay, and each of these combinations, okay, each and every step that you take in trying to get to a solution, we call it as a state, a position, as we've seen in the case of the toddler. So problem statement, along with the initial state where we're starting from and where we want to be, that's my goal state. Okay, and then how can I get there? What are the moves that I can make? What are the steps that I can take? Can I take a right turn? Can I take a left turn? Can I come back? And so forth. So these are all of those operators or actions that I can perform are allowed within that problem solution. Everything put together, okay, everything put together is a solution space. Now let's formulate a problem. What is the problem at hand? What is it that we're trying to do? So need to be very clear on that, right? What exactly is to be done? And then the solution, where we want to be. How do we identify what the solution is? Remember the tester part? That tester is actually your solution tester. Whether that new combination that you tried or the new state of the buttons, okay, or in the case of search for the cheese, what is the location of that mouse? And then how much time do we have? So what do we mean by that? We need to know what is the max time available to resolve something. We might be able to design a house, a perfect house, okay, that satisfies you and your family. That might require, 6 months just to come to that design, for instance. Do you think you have this kind of time? So nobody has. So the important thing is, first of all, the time constraint. You don't have infinite time. Resource availability. What kind of resources can you use, do you have at your disposal in order to solve the problem? What are the rules applicable? Okay. What does the problem tell us about the rules? Okay. What I can do, what I cannot do, what you can do, what you cannot do. Okay. And so forth. Time, for instance, not infinite, but in the case of the house, you might want to say, it must get to the cheese as soon as possible. It might die, for instance. It might die away. It's too hungry. The other thing that the problem statement can tell us is about the location where you are. As I said, the actions permitted, left turn, right turn, move forward, backwards, and so forth, backtracking. So all of this put together gives us a feel of the problem. Okay. And the constraints, meaning where the button, toddler button is, or cheese, the status cheese, where it is, the combinational lock, all of these get a feel of the problem, what the solution will look like. So ultimately, what do you want to do? You want to be somewhere, but you're not there. So you need to know where you are. That's your location. Where you want to be is where you want to be. That's the goal. Now, each of these have a representation. And that goal statement represents the solution of the problem. So once again, I've said this before, if you put all of these together, you have a start condition, what we call as a start state, where you are at the moment, and I want to be 3 steps away. This is where I want to be. This is my goal state. The steps in between that I take, okay, are those intermediate stages of the search. Each of these must be represented very clearly, and the controls, the movement that I'm making, right or left, or forwards or backwards, or turning around, all of these I must know whether I'm allowed to do that or not. Okay. In this studio, for instance, there's a limitation how far I can go, right? So if I were to solve a problem, I must know, I have a fear of the problem, all the constraints applicable, the rules applicable. And very interestingly, all of these put together, all possible conditions. So I'm here, say I'm 3 steps away from the solution. So if I were to represent a solution space for this movement, I only need about 4 representations representing each of my move. So the important thing is representation, the goal state, the start state, the operators, things that allow me to move. So we formulated an example for you, what we call as a 2-1 problem. And let's see how it works. If you can see what we have, what we're trying to do is define a problem statement for this 2-1 problem. And then what is the state and what are the constraints. Now looking at the graph, at the diagram that you have, we have a set of tiles, okay, with 5 positions on it. And we have 2 1s and 2 2s as we see on the graph. Okay. We have 2 1s on the left and the 2 2s on the right. Okay. And there is an open space in the middle represented with that, say, question mark or a blank. So there are 5 positions, 4 filled up, 1 unfilled, right? And what we want to do is, we want to move from where we are, which is the start state on the left, and we want to move to the goal state, which is on the right. Okay. So start state and the goal state. So what we want to do is move the 2 1s to the extreme right and the 2 2s on the extreme left, right? That is our goal, where we want to be. What are we allowed to do? We are allowed 2 basic movements. One is called a slide, the other is called a hop. Slide means you can move those numbers to the very next one. That means sliding from left to right or right to left. That's a sliding movement, the operator here. So that's a legal move, the legal operator, a slide. And the other one is a hop, which means that you can cross over, you can leave one next to you and step over it and move to a next open slot. Now, in this given position, what we have, the limitations are that the ones can only be slided or hopped towards the right, and the twos can be slid to the left or hopped to the left, but not the reverse. So if you make a wrong move, in the sense, if you try to slide one of the numbers 1 on the left, you're not allowed to do that. And you can't move the twos, any of the twos, to the right, whether slide or hop. So it's no backtracking. We can't come back. These are those constraints, okay? The legal moves. As you can see, the start space as depicted and the goal state as depicted. And of course, the aim is to reach the goal as we said before. The 2 coins, which is the 2 rupee coin and the 1 rupee coin, or just the numbers. So you know the operators, slide, and constraints are that you can't backtrack. Ones go on the right only, the twos go on the left only. Now let's try out a few combinations. If I were to give you now and ask you to actually find a solution, what you will do is you'll try to somehow do a random thing and violate the rules to come to and understand the problem. But here we're trying to actually see how it actually happens. Let's try out a few random trials, okay? So trial 1, 2 ones on the left and 2 twos on that. That's the start state. Let's slide one of the twos to the left, okay, which is, as you can see, the new state. Now, what should we do next? What we do is you've moved the 2 to the left and you opened up an open space on the right, so you can hop the 1 from the left to the right, okay? So you see 1 open space, 2, 1, 2. That's where we are. Then you move the 2 to the left again. You slide the 2 in the middle to the left. So the open space now is in the middle. So you have 1, 2 on the left and 1, 2 on the right with an open space in the middle. The only thing you can do now is move the 2 on the right, hop it to the middle position, as you can see. So it comes out to 1, 2, 2, 1, and in blank space. What else can you do? You're only left with the 1 that can move to the right. The 1 on the left can neither slide nor hop because 2 positions are all filled up. The only option left is with the 1 that you have with an open space on the right, you can slide it to the right. And that's where it is. Now you can't move the 2s backward or the 1s backward. So you're stuck. That's one trial. Let's try another one. Same start point, 1, 1, 2, 2. Let's say you move the 1, slide the 1 to the right, then you slide the next 1 to the right again. So the open space is now on the left and you're left with 1, 1, 2, 2. Once again, you can't backtrack. That's not your solution, okay? So you're stuck. So now let's see how to build up. So there are no additional possibilities here. Okay, what we're trying to do is build up the solution space. How does it happen? So from your initial state, you have 2 options. You can either move ones on the right, so you draw a new situation, which is your new condition. That is the new problem representation, a state of the problem. Now, is this a goal state? The tester says no. The other option you have is you move the 2 that's on the right, you hop it to the middle, ask the question, is this a solution? The answer is no. And then you have 2 hops there. Then if you look below, you have the 2 slides option in front of you. You try out those, okay, remembering that the ones can only move to the right, the 2s can only move to the left. So in this way, what you do is you slide, hop, each of these options represented with each state of the problem, okay? Each box that you see is one state of the problem. And you have a constant tester working in your mind at the moment, which tells you it's a goal or not. So just like this, keep on using all the options, okay, try out all combinations until you start seeing, now you see the tree growing outwards, and then now you can see the tree growing inwards. Looks like we are coming to a solution, right? Look at this position. You have hopped, you have 2 2s on the left box. On the right one, you have 2 1 on the right, and we're just about there. Okay. Now the last step is a simple, straightforward slide, and as you can see, you have come to your solution. Now the interesting thing I'm trying to highlight is that this is the complete entire solution space of this 2 1 problem. Okay. We started from the root point, the root node as we call it for the tree, and we reached the solution point. And all intermediate states, all intermediate conditions, okay, representations of the problem are actually within this graph. Okay, and this is known as a solution space. So if you understand, if you get this idea, that's very easy then to generalize and think in larger terms. Okay, I would recommend that you think of simple problems and try and formulate start states, goal states, okay, and then all the intermediate steps. I hope you will be able to actually use and consolidate the concept of this.